Okay, chapter 20, part 2 of the lecture. So I'm going to throw in this little bit right here. All right, second law of thermodynamics. If a process occurs in a closed system, the entropy of the system increases for irreversible processes and remains constant for reversible processes. It never decreases. All right, entropy increases in a closed system for irreversible processes, remains constant for reversible processes. The way we sum this up is delta S is always greater than or equal to 0. All right, and as we get towards the end of this, maybe this will begin to have some intuitive sense to it, but we start with delta S is always greater than or equal to 0. Okay, now tuck that away, keep it in mind. We're moving on to engines. A Carnot engine is in an ideal engine, all processes are reversible and no wasteful energy transfer occurs due to, say, friction or turbulence, right? So nothing lost. Well, that's not where we live, but here is what a Carnot engine does. If you have a Carnot cycle, it has an isothermal heat absorption part, which is here from A to B. So isothermal means temperature is constant. Heat is coming in. We're expanding because heat is coming in. And then there is this adiabatic expansion that occurs here from B to C. Adiabatic means very simply that no heat is going in or out, right? Then there is this isothermal contraction. Better look over here. Isothermal contraction. Heat is coming out during the isothermal contraction. And then there's this adiabatic contraction in which no heat goes in or out. Now, positive work is done during these first two segments, and then negative work is done during those last two, right? And so that leads us to total work done in a Carnot cycle. It's just coming from, hey, look, we had energy come in, we had energy come out. Total work that could be done then has to do with the difference in the amount of energies. And the absolute value signs here are because the cycle can run one way or another, and it really comes down to, is the work being done by the system or on the system, and we're kind of getting rid of the signs for the moment. All right, if we look at this same thing on a plot of temperature versus entropy, all right, isothermal process is constant temperature, and then in the adiabatic process, that's constant entropy, because remember, entropy, change in entropy is dq over T, and since there is no heat going in or out, this is a constant entropy change, and we're back to, the work being done here, right? Or the change in entropy here. The change in entropy here is the change in the entropy in the hot side, change in entropy to the low side, right? QH over TH minus QL over TL. But since it's a cycle, we start at state A, we go around, and we end up back at state A. Because it's a cycle, QH over TH equals QL over TL. All right, these are equal. Total heat coming in, total heat going out, temperature at the high side, temperature at the low side. And we can then write the efficiency of an engine in terms of these. Right? So the efficiency of the engine is really just the work done, right, by the engine divided by the total amount of energy input. If it was a perfect engine, this is 1, but those don't happen. So what we end up with is the efficiency of a Carnot cycle is QH minus QL over QH, or 1 minus QL over QH. Well, we already know from the Carnot engine QH over TH equals QL over TL, and so we go down to here, we stick that in, right, and we get the efficiency of a Carnot engine is 1 minus temperature at the low side divided by the temperature at the high side. So the efficiency of a real engine can never be 100%. And we have here, no series of processes is possible whose sole result is a transfer of energy as heat from a thermal reservoir and the complete conversion of this energy to work. In other words, there is no way to completely utilize all this energy and convert it all to work. Not going to happen. There is one other kind of engine out there that's occasionally used. They're not as efficient as Carnot engines, but it's occasionally used because they're quieter than Carnot engines. And this is a simple Stirling engine where you add in heat and then you have a constant volume process where you're changing the pressure and taking heat out, and then you take heat out on the low side, and then you have another constant volume process where you're putting heat back in to take the pressure up. So you have your isothermal expansion, you have constant volume, you have isothermal contraction, and constant volume. And this is a Stirling engine. Again, less efficient than a Carnot cycle or Carnot engine, however, quieter in general when they're built. Quieter engines. Okay, so after talking about an engine, we're going to talk about a refrigerator. And what is a refrigerator, right? A refrigerator is a lot like a Carnot, well, is really just a Carnot cycle run backwards. So you're going to take heat out of the low temperature. You're going to do work on the system in order to make that heat go into the high temperature. So this is inside your fridge, and this is where your cat lays down in front of your fridge. All right? So you're pulling heat out of the fridge by doing work, and then that heat goes out into the high temperature reservoir. So in an ideal refrigerator, all processes are reversible. There's no wasteful energy. And, okay, how do you judge how good a refrigerator you have? Well, what's the goal of a refrigerator? Pulling heat out of the low temperature. What do you have to do that? To do that, you have to do the work, right? So the coefficient of performance, we call it, for a refrigerator is the amount of heat you get out per the amount of work you do to get it out. So just Q low over W is the coefficient of performance for a refrigerator. And a Carnot refrigerator, Carnot engine operating in reverse, this is just K equals TL over TH minus TL. Now, let me go back to the Carnot cycle, right? This is a heat pump, and if you run it the opposite way, then you're doing work on the system and it becomes a refrigerator. Okay, so we have our coefficient of performance of our Carnot refrigerator, and okay, entropy and a perfect refrigerator. If we had a perfect refrigerator is one where we would not have to do any work, right? We have heat that comes out here and heat then goes into the high temperature. That would give us a delta S, which is minus Q over TL plus Q over TH. And since TH is larger, the positive term is smaller, and so delta S would be zero. Less than zero, pardon me. Delta S would be less than zero. And so the consequence is no series of processes is possible whose sole result is a transfer of energy as heat from a reservoir at a given temperature to a reservoir at a higher temperature. All right. So if we accept that delta S has to be greater than or equal to zero, this can never happen. Okay. Last. No real engine can have an efficiency greater than that of the Carnot engine when both engines work between the same two temperatures. Right, how do we get to here? It's pretty simple actually. Suppose we have this engine over here that's more efficient than a Carnot engine, right? Then we can actually come over here and build a Carnot refrigerator with that efficiency, and this then would this would then move a net, right? Net, because this is more efficient than this, you would move a net amount of heat from the low to the high side for no net work. All right? The total heat transfer would be from here to there, and you could tune it to where there was no net work and end up with a perfect refrigerator. So the consequence of this is simply that, and this is for those that have earned a math proofs, we've proposed something, hey, this is more efficient than that. We get to something that's impossible, and we say, okay, that means this engine can never be more efficient than a Carnot engine. And that is the end of this portion of the lecture.